Avdhesh from National Institute of Science Education and Research, Bhubaneswar. I will talk about speed dynamics in relaxation time approximation. And this talk is based on these references, and these are my collaborators. I hope they all are there. So let me begin my talk with the motivation. So we all know that nuclei colliding at the ultra-relativistic energies, they create a firewall of huge orbital angular momentum. It can be of the order of 10 to the power 5 h bar in case of strict UU collision at 200 GeV at an impact parameter of 5 Fermi. So initially, the system's total angular momentum is given by the orbital angular momentum. Later, some part of this orbital angular momentum can be transferred from transfers to the spin part, keeping the total angular momentum intact, maybe due to the spin orbit coupling. So this may induce spin polarization similar to the magneto-mechanical one-net effect, as shown here. That if you rotate unmagnetized, metallic object, then the spin gets polarized and you observe net magnetic field. So in case of heavy ion collision, you expect the emerging particles to be globally polarized with their space on average pointing along the system's total angular momentum. So this is the schematic view of the polarization of particles in the non-central heavy ion collision. Indeed, the average spin polarization has been measured by RIC star collaboration, and the study is featured at the cover page of this journal. You can see there is a net polarization of the order of few percentage, and it decreases with respect to the collision energy. Present phenomenological prescriptions that are used to describe the data make use of the hydrodynamics, which deal with the spin polarization of the particle at the freeze out. Now, what is hydrodynamics? The hydrodynamics is a combination of local thermodynamic equilibrium and the conservation laws. In this table, we show the governing equations for the ideal hydrodynamics and the dissipative hydrodynamics, which is written in the Landau frame. And you can see in case of the ideal hydrodynamics, you have a 6 unknown, and you have a 6 equation if you include the equation of state. So the equation, the system of equation for the ideal case is closed. You can solve them. However, in case of the dissipative version, due to this dissipative quantities, we have additional 9 equations. So, so the system is not closed. We need 9 more equations for this dissipative quantities. So for the simplest Navier-Stokes case, the expression for these dissipative quantities are given by these expressions. Here, this nabla mu is used for the transverse gradient, and the sigma mu nu is the shear flow tensor. While this this eta and zeta and kappa are the transpose coefficient, which we call the shear viscosity, bulk viscosity, and charge as a heat conductivity. Now the question is that how these equations can be used to calculate the spin polarization. So the idea is the thermal vorticity, which in the local equilibrium you can take it same as the spin polarization tensor. I refer this reference for this statement. And the thermal vorticity is defined in terms of this beta field. So the algorithm to calculate the spin polarization using this hydrodynamics is as follows. So first you run this hydrodynamics either ideal or viscous, and then you calculate this beta mu field at the freeze out hypersurface, and then you calculate thermal vorticity, and you consider it as a spin polarization tensor, and then you make prediction about the spin polarization. So this method works well, and this describes exactly, I mean, you can fit this data for the global polarization exactly, but there is a problem in explaining another experimental observable, that is the longitudinal spin polarization of particles as a function of the transfer momentum. So in the slides we show the experimental result for the on this left panel we show the experimental result for this longitudinal spin polarization, and on the right panel is the theoretical result. So in the experiment, this longitudinal polarization is measured by the ensemble average of the cosine of the polar angle of the proton momentum in the rest frame of the lambda. This as a function of azimuthal angle relative to the second order event plane is shown here. And this is the theoretical result, which as a function of the transverse momentum is shown here. Now, in this last panel, if you go along this upper half cycle, which corresponding to the 0 to pi by 2, and if you think intuitively, then this upper half cycle should correspond to this quadrant. So here you see this is positive, the spin polarization, and here it is negative. And similarly for the second, the lower half cycle, you see this is negative, here it is positive. So there is a discrepancy in explaining the quadrupole structure using this hydrodynamic model. Some solution to this problem can be provided in these references by Bolosing, where you use the blast wave model, and then this by PICR hydrodynamic models, and then this Carrel kinetic theory. And interestingly, thermal model with the projected vorticity can also, provide some solution. You can see that if you use the projected thermal vorticity, then you can actually change the sign of the quadrant. So this puts a doubt of using the notion that the thermal vorticity is same as the spin polarization tensor in the local thermodynamic equilibrium. Some support to this also comes from the non-equilibrium statistical thermodynamics by Avdhesh, which says that the spin polarization and the thermal vorticity are same holds only if your energy momentum tensor is asymmetric. If it is symmetric, then the same is not true. So we need to include spin in the hydrodynamic framework. And one of the reasons to include the spin is that the present hydrodynamic frameworks are limited to the calculation of the spin polarization at the freeze out. And hydrodynamics should explain the space-time changes of the polarization. So the first thing one can think if one to include the spin, that for the particle with spin, apart from the conservation laws of charge energy momentum tensor, one should ensure the total angular momentum conservation. So the conservation of angular momentum is non-trivial. New hydrodynamic variable should be introduced. I call it the spin potential rather than the spin chemical potential, as suggested by Francesco in the previous talk. And this we can do by extending the local thermodynamic equilibrium, where we treat the thermal vorticity same as the spin polarization tensor, to the case of the local spin thermodynamic equilibrium, where the two are not equal. So before going to discuss the formulation, let me discuss the angular momentum conservation. So So the orbital angular momentum for a particle with momentum p is expressed by the cross product with position with this momentum, and it's and its dual is a second rank tensor, and you can obtain by contracting this by this Levi-Cita symbol. Both are equivalent in the sense that they have a equal number of degree of freedom, but the later is advantageous as it has a clear geometrical interpretation as a plane element. So in the absence of your external torque, this orbital, if we don't have spin, this orbital angular momentum should be conserved, and this is valid for the non-relativistic system of particles. For the relativistic system of particles, the orbital, so we should use this 4 momentum and this 4 space-time coordinate. And for fluid, now if you have a fluid, then this momentum has to be replaced by generalized fluid momentum, which is energy momentum tensor. So for fluid, this orbital angular momentum is a 3-rank tensor. Now, keeping in mind that energy momentum tensor is conserved, this equation will give this equation for this orbital angular momentum. And classically, this energy momentum tensor is symmetric, so orbital angular momentum is conserved. Now, if we have a medium constituting with intrinsic spin, then we must have a total angular momentum, which is a sum of the orbital and the spin. Now, and this total angular momentum should be conserved. Now, the conservation of this total angular momentum will imply that the derivative of the spin tensor is again given by this expression. So from here, if you see that energy momentum tensor is symmetric, then your spin is conserved. Thus, the required conservation law for a fluid with spin degree of freedom are the charge conservation, energy momentum, and spin. Initial step to formulate the hydrodynamic spin has been already made. For example, there are the formulation which is based on the generalization of the standard scalar function in terms of 2 by 2 Hermitian matrices in the spin space for each value of the space-time position and the 4 momentum, and this formulation is actually based on the particular choice of the energy momentum and spin tensor, namely this canonical version. And later, there is some work using this Wigner function technique. We have clarified that the use of Tetroth 1 log 1 and 1 verb DLW form of this tensor over the canonical version. And also there are some more work in this direction by Hattori in entropy current analysis, and then by Nora et al. In this Wigner function, and by Shi, and then Toreri, the Lagrangian technique, and this holography technique by Umu. Finally, some applications can also be seen based on this GLW based hydrodynamics to calculate the spin polarization. Basically, this application for this we have used the toy model where we consider the Bjorken flow. to calculate the spin polarization. We didn't get the correct result because the spin polarization is connected with the deformation in the transverse direction, the elliptic flow. Hopefully, we will see a more accurate application that is in full 3+1 dimension soon. So, in this talk, using the classical treatment of spin degree of freedom, I will discuss how kinetic theory description allow us to construct the perfect fluid hydrodynamic with spin. And then later, using the relaxation time approximation of the collision term, I will also discuss a simple extension of this framework to the case including dissipation and show some results for a complete set of new kinetic coefficients that characterize the dissipative spin dynamics. So the classical treatment of spin, one introduced the intrinsic angular momentum tensor for the particles, which is connected with the 4 momenta and the spin 4 vector of the particle by this formula. And this intrinsic angular momentum tensor is antisymmetric. You can clearly see with this Levi-Setter symbol, and this satisfies Frenkel or Bardson-Hoff condition. And this spin 4 vector can be obtained by inverting this equation, and this expression for the spin 4 vector can be obtained. You can see that spin 4 vector is also orthogonal to the particle 4 momenta. Therefore, in the particle rest frame, where you have 4 momenta, which is like this, you have only a special component of the spin 4 vector with this length given by the Casimir operator. The next step is to construct the equilibrium distribution function. To construct the equilibrium distribution function, one has to identify the collision invariant of the Boltzmann equation. So how to do it? So apart from this 4 momentum and the conserved charges, for particles with spin, we have a total angular momentum conservation, where the total angular momentum is the sum of the orbital and the spin part. Now, the locality of Boltzmann equation suggests that this orbital part can be eliminated, and we can consider the spin part separately. Thus, for elastic binary collisions of particles 1 and 2 going through 1' and 2', one should have sum over initial spin angular momentum to be equal to the sum over final spin angular momentum of the particle. Now, the solution of this equation admits two types of solutions: either the sum of the spin 3 vectors or their difference is 0. This means that we can interpret the collision in the spin singlet or the spin triplet state as shown here in this picture. So, if our collision term allow for such kind of processes, then we should include the spin angular momentum conservation. And this implies, so this suggests that we can introduce spin-dependent equilibrium distribution functions for particle and antiparticle of this form. Now, knowing this equilibrium distribution function, now since we have included the spin in this distribution function, so we have extended the phase space. So the integration on the spin variable can be done using this covariant phase space measure, where this normalization is chosen such that the measure integral of this phase spin measure is 2, and the momentum measure is given like this. Now, knowing the equilibrium distribution functions, the conserved charge current can be obtained by this definition. Remember, due to the spin variable, we have extended the phase space. So instead of the three momentum, we have to modify. We have to take into account the spin measure also. So now, if we use the equilibrium distribution functions as defined earlier, then we can obtain this expression for the equilibrium current, equilibrium charge current. Now, for large values of the spin polarization tensor, one can see, as reported in this paper by us, that the system becomes anisotropic in momentum and requires special treatment, and this also breaks the perfect fluid picture. So we consider only the case of small values of omega. In this case, this spin integration can be carried out very easily, and if you carry out the momentum integration also, then you obtain this form, this perfect fluid kind of form of this charge current, where this the density is given by this expression, and this N0 is the number density of the neutral spinless Boltzmann particles, which is given by this expression here. Z is the ratio of particle mass to the temperature. Similarly, one can obtain the energy momentum tensor using this definition, and if we consider the small omega, that is in the linear order, then the integration over spin and momentum will be this perfect fluid kind of definition of energy momentum tensor, where this energy density and the pressure are given by this expression. And for the spin tensor, so the spin tensor can be calculated by the expectation value of the internal angular momentum tensor. So we use this definition for the spin tensor, and then in the leading order omega, we carry out the spin integration first and then the momentum integration, and we obtain this equilibrium spin tensor, which agrees with the Leuven and Wirth expression of the spin tensor. And here this auxiliary part of the spin tensor is given by this expression, and this square brackets are used for the antisymmetrization of the indices, and coefficients are listed here. Now let's look at the entropy conservation. So to construct the entropy current, we adopt the Boltzmann definition in this extended phase space. So then if you substitute the equilibrium distribution functions, then we get this expression for the entropy current, and it can be shown using these conservation laws of the energy momentum charge and spin. It can be shown that this entropy is conserved. Note that this expression is exact and valid for all order in omega, and also from this expression of the entropy current, you can notice that since S equilibrium is proportional to omega, so the contribution to the entropy production actually comes from the spin polarization tensor terms, which are quadratic. This means that no effect of spin polarization on the entropy production in the linear order in omega. So this is also one of the important results. Now let's look at the dissipative correction. So To obtain the dissipative correction, we use relaxation time approximation for the collision term in the classical kinetic equations, which are originally introduced in this reference. And this collision term in the relaxation time approximation has this form. Now, we consider a simple Chapman-Enskog expansion of the single particle distribution functions around its equilibrium values in powers of the space-time gradient, and then up to the first order space-time gradient, the following expression for this corrections to the equilibrium distribution function can be obtained. This generates the dissipative correction, the dissipative corrections to the charge current, equilibrium charge current, and spin tensor, and the energy momentum tensor. So, to calculate the dissipative corrections, let's take the moment of the appropriate moment of the transport equations. If we do so, we get the following evolution equations for the charge current, for the currents, all the currents. And here the difference of this current on the right hand side can be written is the dissipative corrections in the current, the charge current and energy momentum and the spin tensor. Now, since the energy momentum, the charge current, energy momentum tensor and the spin tensor are conserved, this implies that the dissipative corrections to the charge current, energy momentum tensor and the spin tensor should follow these conditions. And these conditions for the charge current and energy momentum tensor are known in the literature for a long time. However, here we see this spin tensor also follow the similar conditions. So we say that these are the extended Landau matching conditions if you take into account the spin degree of freedom. Now, the dissipative corrections to this charge current and energy momentum tensor can be calculated by these moments of this distribution function. Now, if you carry out the integration on the spin and the momentum variables, then we can obtain the following expression for the dissipative corrections on the charge current and energy momentum and spin tensor. From here, we can notice that the dissipative corrections does not include dissipative corrections in the charge current energy momentum tensor does not include the term which involves the gradient of the spin polarization tensor. Also, this coefficient beta and beta pi also does not carry any information related to the spin polarization tensor. So our main result is the expression for this delta F lambda mu. We suggest that the non-equilibrium part of this spin tensor is produced by the thermodynamic forces such as the expansion scalar theta and the gradient since I is the ratio of mu by T, so the gradient of the ratio of the chemical potential to temperature, and then the shear flow tensor and the gradient of the spin polarization tensor. Thus, the dissipative spin phenomena are connected with those leading to the formation of the bulk pressure, because the theta is connected to the bulk pressure, and diffusion current because this gradient is connected to the diffusion current, and the shear flow tensor is connected to the shear stress tensor, and interestingly the gradient of the spin polarization tensor. And these are the expressions for the transport coefficients, and these are the transport coefficients appearing in the dissipative part of the spin tensors. You can see these are the combination of the flow velocity, spin polarization tensor, and the G mu nu or delta, the transverse flow vector. And here we do not list this scalar coefficient because these expressions are quite complicated, and you can see this expression in this reference. So now I will summarize. So what I have talked about is using this classical treatment of spin degree of freedom. We have outlined the procedure to formulate the perfect fluid hydrodynamic with spin. We have found that the contribution to the entropy protection coming from the spin polarization tensor are quadratic in omega mu. And then using the relaxation time approximation of the classical kinetic of the collision term in the classical kinetic equation, we discussed the formulation of the dissipative relativistic hydrodynamics for particles with spin, and then we saw that in the leading order in omega mu nu, the transport coefficient related to the energy momentum tensor and charge current remains unchanged, and the spin dissipation is caused by the scalar expansion, the air stress, particle diffusion, and the expected spin diffusion. And we also presented the results for a completely new set of kinetic coefficients that characterize the spin dynamics. And in future investigations, it would be interesting to analyze the role played by the various coefficients to find out which kind of corrections they imply for the spin tensor. The complicated tensor structure of the spin kinetic coefficient may lead to various interesting phenomena. And the other thing is that can be done is the inclusion of the mean field in this approach. So thank you for your attention.
Thank you, Avdhesh, for finishing in time. And now we can have some questions.
Nice, just short question.
Okay.
Have you published your result already, or you are in preparation?
Sorry.
I'm sorry about this new dissipative transport coefficient in spin hydro. Have you published that result?
Yes. So so the results, these are already on archive. They are under review actually. We already sent for the review. So these results are in these references. You can look at these references.
Okay, thank you. Yeah. Okay.
Yeah.
Any other questions? Okay, Sugong.
Oh, hi, nice talk. Could I say that in your formalism, the spin current is just like a two-index charge current, and the omega mu nu is just like a two-index chemical potential?
So spin current is three-index tensor actually.
Yeah, I know, but you have S lambda mu nu, but this mu nu index actually seems does not play much role in the whole derivation, isn't it?
Maybe Amaresh or Wojtek can explain about this question.
Yeah,
I mean by that some indices do not play the role. It's,
your S lambda mu nu is like charge current with mu nu as indices, and omega mu nu is like chemical potential with mu nu indices.
Omega is indeed something like the spin chemical potential, and usually people take it as the thermal vorticity. Yeah? In our case, it's independent and fulfills some dynamic equations of hydrotype. But
yeah,
all the indices are really, mixed after a while when you do the calculations, and really the structure is very, very complicated. Although, these are algebraic expressions, but Avdhesh didn't, dare to show them because they are really very lengthy and complicated.
I can imagine.
So I think there's nothing like that, these two antisymmetric indices kind of factorize, and all dynamics is kind of simplified and factorizes in some way. All the indices kind of are mixed in the dynamic equations.
Yeah. And also in order derivation, how the omega mu nu is treated as a quantity of order 1, right? I mean, suppose we do the hydrodynamic gradient expansion, so omega mu nu is treated as a order 1 rather than order, say,
omega mu nu
gradient.
Omega mu nu is dimensionless in our case, because somehow this is how we define equilibrium distribution. And omega mu nu is a dimensionless quantity, so we can always make expansion in omega mu nu because it makes sense. It has no dimension. But there is, of course,
yes. I mean, when you do the expansion in omega mu nu, and also suppose you do the gradient expansion,
yes,
so these two expansion are considered. I think
they are
the same order.
Yeah, I think they're independent because I think the
Okay, then I understand. So you do two independent expansion.
Yeah, I would say even 3 because we first make the semi-classical also expansion if we want to derive, the equations from the equation for the Wigner function. So there is something like the semi-classical expansion with omega treated as a dimensionless quantity, which can be large or small. Actually, I have general remark that this polarization, we call it spin polarization tensor omega, but in other cases, people have thermal vorticity here. This quantity should be always small. In the case of thermal vorticity, I think you have the dimension, so you have to multiply it by the Planck constant. But this should be small because otherwise, the spin tensor which comes from this famous Becattini's formula is not bounded. It should be between 1/2 and 0, or between 1 and 0. But it should be normalized and finite. And this expression usually is, you don't see that it is kind of bounded. If you have high vorticity, then it explodes. So it's obvious somehow that the whole formalism we are discussing during this workshop probably is really for very small polarization effects, which is actually not very bad because the data show that the experiment, that the effect is small. So
that's true. Yeah, that's true.
So I would say that we have 3 kind of expansions which are independent in this approach. There is, of course, this basic expansion or locality of the collision term, which is probably the strongest one.
I see.
Okay, so next question by Dave Ho.
Okay. Hi, thank you very much for this talk. My question is, does the relaxation time on your right-hand side also depend on the spin?
Here, the relaxation time we take is constant.
You take some constant, but in principle, if you release it should also depend on the spin, right?
Yeah, in principle, it is possible, yeah. But here we assume it is constant.
All right, thank you.
And then Nora? Nora, you want to ask the question?
Yes, so Vertex just said that you do the H-bar expansion independent of the gradient expansion, is that right?
Sorry, could you repeat? I could not understand it properly.
Yeah, I would say that, okay, we make H-bar expansion as everyone does for the Wigner function. Only
Yes.
the difference is that, as you know, that we say that omega starts with, you know, in your language, it will be at higher order in H-bar. Because your omega always includes H-bar.
Yes.
So somehow, okay, if we want to switch to your approach, we would say that our omega is something like H-bar times the new omega. But you know, the total thing should be dimensionless, like the rate of chemical potential over the temperature. So in our case,
and your gradient expansion, is it independent of your H-bar expansion?
I think usually this goes together as in your case, yeah. But I would say.
But you go to first order in gradients, right?
Right.
And to zeroth order in H-bar, is that right?
Right, right. So we have leading order and next to leading. So zero, then first order in H-bar.
So you have the first order H-bar or not? Do you have the first order H-bar?
Yeah, we include the zeroth and first order terms in the expansion in H-bar to derive equations, yeah?
Also in the form of pure GLW spin tensor?
And the spin tensor goes like with H, yeah? So the spin tensor goes like H times omega, which omega is dimension.
But this H does not go with the gradient. So if you make gradient expansion, you cannot count this one H in front of them as lambda mu, I think.
You know, in this hydrodynamic expansion, I think there is no H-bar, you know, in the hydrodynamic expansion.
Yes.
So I would say, I'm not sure whether you agree with me. I think we do what you do, but somehow we say that, okay, I would say that, okay, we could start like as you are starting, but then we say that that your omega is something like omega over H-bar. So somehow H-bar cancels and we are left with our omega, which is dimensionless. So it probably is a kind of argument that we have many particles with spin and somehow the number of particles compensates the smallness of H-bar. Like in the paramagnetism that you see classically effects which are purely quantum. That you have many particles and because you have many particles, then you see, you know, effects from H-bar, like in the paramagnetism.
Okay, thank you.
Okay, yeah. So maybe the next question by Masood.
Hi.
Hi.
I already wrote my question here. You have epsilon plus p equal to Ts, yeah?
Yeah, epsilon plus p equals here, yeah, Ts, yeah.
But do that. What?
No. Actually, I think these are auxiliary variables. You know, so we have.
Yeah, these are auxiliary
This
variables.
is epsilon 0. Yeah, okay.
These are auxiliary variables.
Yeah, this is without the C part. Yeah.
Right.
Okay.
So usually you have two other terms. You wrote that epsilon plus p is Ts, yes. But in addition we have mu times n plus, you know, omega minus s.
Yeah. Thank you.
Okay. So last question by Jun.
Yes. When you write down the boson equation, you use the RTA, right?
Yeah.
So your S, you use the tensor form of S or vector form of S?
Yeah, for the spin, yeah. S is, okay. Which S you are talking about? The intrinsic angular momentum or
No,
spin?
no. This is the S variable. It's the spin.
Oh, F.
Spin
Okay, this. The spin variable. Yeah, this is the intrinsic angular momentum tensor.
But
Yeah.
you mean if you
vector.
use I mean S vector and S tensor is related to P. I mean, so
Yes,
it's
yeah. So,
You know,
so
S
which
is
is independent? I mean, what is independent?
S is a 4 vector here, you know, so the distribution function depends on space-time coordinates, momentum, and the four vector S.
I see. So S is a vector. Then in your
It's a 4 vector which is perpendicular to P, and actually it's also its length is fixed. So there are 2 degrees of freedom.
Yeah. I see. So this is the classical analog of the spin, right?
No, this is classical analog. You know, the idea is, okay, if you measure the polarization, somehow you can measure along different directions and you get the mean value and somehow the mean direction. So the classical spin has the effect of making many quantum measurements which give you the mean direction and the magnitude. So actually when, so if you have, you know, the magnitude 1/2, it means that you have pure state. And if you have a smaller magnitude, it means that you have mixed state. Yeah. So in heavy ion collisions, we deal with mixed states because this polarization is always very small. Yeah.
I see. So therefore, your equilibrium form, you write down equilibrium form. You have to use the tensor part, the tensor component, right? The tensor.
Yeah, because you know, this is the quantity which is conserved. Maybe Avdhesh, you could go to our equilibrium function. Yeah. Okay, you know, because actually the tensor S alpha beta, this is the quantity which is conserved.
Okay.
So not
but this tensor is related to this vector through P. For E, if P is different, S alpha beta should be different.
Okay, so the tensor S is conserved because this is the angular momentum, which for local collisions is conserved because angular momentum is 0. So this enters, you know, the equilibrium distribution function where we have usually collisional invariants. Yeah? So you know, momentum is conserved, charge is conserved, and
then your alpha, your S vector should be dependent on P, right? If
S is constrained, you know, so it's like saying that the momentum depends on mass. You know, momentum is constrained by the mass. So the 4 vector S is constrained by the condition that P dot S is 0, that these are orthogonal.
But S vector is related to S tensor through P.
Right. So this is this Matheson, you know, formula from, you know, 36.
Yeah. So I mean, what is the independent on P and what is dependent on P? I mean,
okay, so you have 3 degrees of freedom in the momentum, and you have 2 degrees of freedom in S.
Yes.
Because S is orthogonal to P, and the length of S is fixed. You know, so if you have, you know, so S is.
Say if you treat the S vector is independent of P, then S alpha beta should depend on P, right?
Okay, the convenient way is to have the distribution function which depends on the PS, and then introduce, you know, this measure the momentum which takes into account the constraint. Like we love to integrate over the momentum and include the delta function, delta of p squared minus m squared. Yeah. So now I don't know what you mean somehow. It's
okay. So
yeah. Let's talk it later.
Yeah. Right. So there was one question by Golam in the chat, and Dirk already seems to have answered it, as well as the discussion regarding S being orthogonal to P was also being made. So one quick question from Enrico.
Yeah. Hi. Yes. not just, I'm not sure whether I understood. So the deviation from equilibrium, you count it as the same and independently than the h-bar expansion, right? The expansion from equilibrium. Do I understand correctly? So when you write the distribution function as f equilibrium plus delta f in slide.
Okay, we do first, you know, this, this was not discussed here, but you know this, probably our paper with, there's where we just used Wigner functions and we made the semi-classical expansion. But then, you know, in the semi-classical expansion, our omega is kind of, is a dimensionless quantity, like mu over t. So it's the spin potential. And so we don't care if we make expansion in h bar, omega is just a number, you know, dimensionless number. So at some point we want to have it small, but we can make it small because it's just dimensionless quantity. Yeah. So in this sense, we have two expansions. One in h bar, of course, this expansion in h bar goes with the gradients, and one should compare different terms because this is not expansion in dimensionless quantities. Even if you multiply h bar by the gradient, it still has the dimension. Yeah, you have to have the gradient with x and p, and then it would be expansion which is dimensionless. So, you know, vaguely speaking, we have expansion in h bar with omega, which is dimensionless. Then we say omega is small. And then when we go to hydrodynamic equations, which follow from this relaxation time approximation, we make expansion in the gradient, in the gradients, but then the gradients should be compared to the size of the system, in the sense that you have to construct the quantities where you have the gradient, for instance, of the temperature divided by the temperature, and this is multiplied by the size of the system. So, for instance,
and this for you has nothing to do with h bar, right?
And this is independent. This is expansion in the Knudsen number. So I think we have three expansions put together. Mm-hmm. So these are kind of assumptions regarding the expansion, but the most crucial thing is this local thing, which is kind of approximation within the Boltzmann equation. Because if you have quantum scattering, of course, you don't have this. You average over all. This is coarse graining, you know, and then what we want to do. And I also interpret your work in this way that we want to kind of make something different from this coarse graining, which is in the Boltzmann equation. Yeah, because
because in our case we treat all the h bar all the same, all the gradients all the same. Also the deviation from equilibrium. So that's the difference.
Right. Of course, you have this attractive feature that you have this coupling, yeah, which we are missing, and we try to check this what comes if we have the collision term and we make this expansion, but we didn't finish the calculation yet. Yeah, I think your approach is really attractive, that you get this coupling between vorticity and polarization. We miss it. We miss it all the time. Yeah. So.
Okay. So we'll discuss. Yeah, we'll keep discussing this.
Yeah, maybe later. Yeah.
Right. So thanks again.